concrete encasement around an electrical duct bank does not add to the derating factor. It can actually help reduce it. The derating factor is a multiplier applied to a conductor's ampacity. This accounts for factors that reduce the conductor's ability to carry current. These factors include, firstly, ambient temperature. The higher the ambient temperature, the less current the conductor can carry. Secondly, conduit type. The type of conduit affects the derating factor. For example, a conduit installed underground typically has a lower derating factor than one installed in the air. Thirdly, the number of conductors in the conduit. More conductors in a conduit results in a higher derating factor. And fourthly, conductor spacing. The spacing between conductors also influences the derating factor. The concrete encasement around an electrical duct bank can help to reduce the derating factor by providing a more stable temperature environment for the conductors. The concrete also helps protect the conductors from damage, reducing the risk of electrical faults. Typically, the derating factor for an electrical duct bank installed underground in concrete is 0.8. This means the ampacity of the conductors in the duct bank must be reduced by 20% to account for the effects of the concrete encasement and the underground installation. To elaborate on ambient temperature, the National Electrical Code, or NEC, specifies temperature ratings for conductors. These ratings indicate the maximum temperature a conductor can withstand without degrading its insulation. When the ambient temperature around a conductor increases, the conductor's temperature also rises. If the conductor's temperature exceeds its rating, the insulation can break down, leading to short circuits, ground faults, and potential fires. Derating addresses this by reducing the allowable current the conductor carries in higher ambient temperatures. This ensures the conductor operates within its temperature rating. Consider a conductor with a temperature rating of 90 degrees Celsius installed in an area with an ambient temperature of 40 degrees Celsius. This conductor can safely carry its full rated ampacity. However, if the ambient temperature rises to 60 degrees Celsius, the conductor's temperature will also increase. To prevent the conductor from exceeding its 90 degrees Celsius rating, the ampacity must be reduced or derated. The NEC provides tables that outline the derating factors for various conductor types and ambient temperatures. These tables help electricians and engineers determine the appropriate ampacity for conductors in different environments. Different types of conduits have varying thermal properties, which affect their ability to dissipate heat. Metal conduits, such as steel and aluminum, are excellent conductors of heat. They can effectively transfer heat away from the conductors inside, helping to keep them cooler. Non-metallic conduits, such as PVC, are poor conductors of heat. They tend to trap heat inside, which can increase the temperature of the conductors. Underground conduits benefit from the Earth's natural cooling properties. Surrounding soil helps to dissipate heat away from the conduit, keeping the conductors cooler than they would be in open air. This is why underground installations typically have lower derating factors compared to above-ground installations. When multiple current-carrying conductors are installed in the same conduit, the heat generated by each conductor can raise the overall temperature inside the conduit. This phenomenon is known as conductor bundling. The NEC requires that the ampacity of conductors be derated when more than 3 current-carrying conductors are installed in a single conduit. The derating factors vary depending on the number of conductors. For example, if 4 to 6 current-carrying conductors are installed in a conduit, the ampacity of each conductor must be derated to 80% of its original value. If 7 to 9 current-carrying conductors are installed, the ampacity must be derated to 70%. The spacing between conductors also plays a role in heat dissipation. When conductors are tightly packed together, it becomes more difficult for heat to escape. This can lead to higher temperatures and increased derating requirements. The NEC specifies minimum spacing requirements for conductors in certain applications. These requirements help to ensure adequate ventilation and heat dissipation. Concrete encasement provides a stable thermal environment for electrical duct banks. Concrete has a high thermal mass, which means it can absorb and store a significant amount of heat. This helps to dampen temperature fluctuations, keeping the conductors at a more consistent temperature. The concrete also helps to protect the conductors from external temperature variations such as changes in air temperature or direct sunlight. This stable thermal environment reduces the need for excessive derating, allowing the conductors to carry more current safely. Concrete encasement provides physical protection for the conductors. The concrete acts as a barrier, protecting the conductors from damage caused by mechanical stress, moisture, chemicals, and other environmental factors. This protection reduces the risk of insulation breakdown, short circuits, and ground faults. By minimizing the risk of these electrical problems, concrete encasement contributes to the overall reliability and safety of the electrical system. The typical derating factor of 0.8 for underground concrete encased duct banks is a general guideline. The actual derating factor may vary depending on specific installation conditions. Factors that can influence the derating factor include the depth of the duct bank, the type of soil, the ambient temperature, and the number of conductors in the duct bank. It's important to consult the NEC and other relevant standards to determine the appropriate derating factor for a specific installation. The NEC provides tables and guidelines for calculating derating factors based on various installation conditions. These tables take into account factors such as ambient temperature, conduit type, number of conductors, and conductor spacing. By following the NEC guidelines, electricians and engineers can ensure that conductors are properly derated to prevent overheating and potential electrical hazards. In addition to the NEC, other industry standards and best practices can provide guidance on derating electrical conductors. These standards may offer more specific recommendations for certain applications or environments. Consulting with experienced electrical engineers and contractors can also help to ensure that conductors are properly derated. These professionals have the knowledge and expertise to assess the specific conditions of an installation and determine the appropriate derating factors. Proper derating of electrical conductors is essential for ensuring the safety and reliability of electrical systems. By understanding the factors that influence derating and following the NEC guidelines, electricians and engineers can prevent overheating, insulation breakdown, and other electrical hazards. This helps to protect people and property from the risks associated with electrical failures. Remember that electrical codes and standards are constantly evolving. It's important to stay up to date on the latest requirements and best practices. This can be achieved by attending training courses, reading industry publications, and participating in professional organizations. By continuously expanding their knowledge and skills, electricians and engineers can ensure that they are providing the safest and most reliable electrical systems possible. So, while concrete encasement doesn't increase derating, understanding its benefits and applying the appropriate derating factors are crucial for safe and efficient electrical installations. Always consult the latest NEC guidelines and consider specific installation conditions to determine the correct derating requirements.